Okay, so we went over this already. Well, welcome. Sorry, I should have said welcome. We went over most of this already. However, I'm just going to do a little bit of a synopsis. Of course, we have our summary statistics, visualization, then analysis, and then we'll jump right into the equations. The questions, conceptual questions. So we have three variables: crime, room, and age being used to predict median value of a home. Okay, so the min and max are used to determine which values we can make a prediction on. Okay, so we're aware of that. We are aware of that from class before. Here is our correlation matrix that shows the relationship between all of the variables with one another. Okay, I didn't say this in class, but along the diagonal, it's one because the correlation with a variable with itself is just going to be one. And so here there are four variables, so therefore we have 4 choose 2, or 4 times 3 divided by 2, 6 different pairs. And we can see these 6 in terms of being positive and then the ones that are negative. Okay, and so ideally, when it comes to our explanatory variables, crime, room, and age, we would want them to be not related to one another. We would want them to be as independent as possible, meaning that the variability that's being explained within the response variable, right, um, is independently explained by each of the explanatory variables. They're independent from one another. Okay, so what I mean by independent are a scenario in which we have independent variables would be, let's say we have the pH of water being poured on a plant and are on plants, and the actual amount of the pH of the soil and rain fall, and we're trying to see if how those two variables predict or impact the crop yield. Ideally, we would want those two variables, and they are independent. You know, the soil type and the actual pH will be independent from one another in terms of having an impact on crop yield. And that makes sense because when it comes to explaining the variability and making predictions, we would want those explanatory variables to not be related to one another. We don't want them to be related to one another because then it's duplicate information. We're not adding new information when we're predicting our response variable. So I want to talk more about that in a moment, but just be aware of that. We would want the correlation, aka the linear relationship between our explanatory variables, to be relatively low. In terms of visualizations, this is what we would use. Again, we saw this already in class in terms of explaining the relationship between all of our variables in the model, response, as well as the explanatories. Okay. And some student asked me one day, will the response always be the first? It doesn't have to be. It doesn't have to be. Okay. And so describing this is more of a negative association, right? This is a positive. I would say this is negative. Okay. Negative, somewhat positive, and somewhat not. Somewhat, it's like negative. But here I would say 1, 2, actually 1, 2, and 3. These linear relationships are there, but they're not strong. Okay, they're not strong. Let's keep going. So then, in terms of our analysis, from Wednesday's class, we should have been able to write out the regression equation from this output. We should have been able to specify the standard deviation of residuals, okay, a model metric. We're using the adjusted R-squared, and I'll tell you why soon. And we should have been able to notify, or at least, recognize the test statistic from the omnibus test, where we're testing all the regression coefficients at once and its corresponding p-value. Okay? But remember just about 30 seconds ago or a minute ago where I mentioned this idea of our explanatory variables being independent from one another. There is a metric that we can use to measure how much our explanatory variables relate to one another. And that is the VIF, okay, the VIF score. So multicollinearity is when our explanatory variables relate to one another. The variance inflation factor allows us to measure the multicollinearity, how much our explanatory variables relate to one another. So the lowest value that we can have for our variance inflation factor is 1. The highest value that we can have is infinity. 1, infinity, 1, infinity. Okay, so a variance inflation factor, okay, again, it's measuring how well our explanatory variables, or not how well, how much our explanatory variables relate to one another. A VIF score that's in between 1 and 4, we're good to go. We're good to go. No problem. No problem here. But a VIF score that's greater than 4, problematic. Okay? So that is important to note. Okay? And so here, I would argue 1, 2, 3, 4, all 3 of these VIF scores signify the actual explanatory variables not being highly related to one another. So it's not a problem here. It's not a problem. Okay? And that's it. There are equations. Of course there are equations. But do we need to see the equations? No. It's just the concept of we don't want our explanatory variables to explain the same variability in our response. So what we want to do is measure the relationship between our explanatory variables, and these VIF scores give us the measurements. And if they're in between 1 and 4, good to go. Above 4, we have a problem. In real life, we'll consider removing one of the explanatory variables based on the criteria, but that won't be evaluated here. Okay, that won't be evaluated in terms of removing. But just know that greater than 4, problem. Okay, so oh wow. All right, so state this is what you already have access to the answer, so I'll go through this relatively fast. But state the variables in this problem as well as the response and explanatory variable. So we already mentioned this. The response variable is median value of the home, and then explanatory variable is crime, age, and room. Okay. So then going from there, how do we visualize this? Okay, since they're all quantitative, these are going to be scatter plots. How many pairs do we have? 4 times 3 divided by 2. So the number of variables times the number of variables minus 1 divided by 2 is going to be the number of relationships. How do we measure the relationships? By linear relationships between 2 quantitative variables. Correlation, what are some properties? We've seen this before. R is in between -1 and 1. We can reorder the correlation, at least reorder the variables, and the correlation will still be the same. All right, so this is nothing crazy. We've seen this before. Okay, we've seen this before. When it comes to something that's different from simple linear regression and multiple linear regression is that we can simply use R times Sy over Sx to find the slope for simple linear regression, whereas finding the actual regression coefficients for multiple linear regression doesn't work that way. Again, beyond the scopes of this class, okay, on how those estimates are actually found, okay? So then here, we did this in class, but it says write out the regression model and from the R output, provide an interpretation of the regression model. We did not do that in class. And now we're going to be responsible to be able to interpret regression coefficients. So here's a regression equation. Okay, I rounded it, of course. Okay, where I specify what x1i is, what x2i is, and what x3i is. And mind you, on the quiz, I did not grade if you did not specify this, but from now on, I will. Okay, so in terms of interpreting the regression coefficients, we're going to interpret 1, 2, 3, and 4. This is the y-intercept. This is the regression coefficient for crime, regression coefficient for room, regression coefficient for age. Okay, so when it comes to y-intercept, this should be intuitive, right? When all the explanatory variables are equal to 0, the average median home value is negative 23.61. Again, this is, I would say it's still uninterpretable because we can't have the value of a home be negative, nor could we have 0 rooms within a house, because inherently a house will have at least 1 room, or at least the sentence tract will have a home with 1 room. Sorry. Great. When it comes to interpreting the other regression coefficients, again, let's play the game. What's the name of the game? Say it to yourself out loud. Pay attention. Put down your phone. Um, Unless you're using it to watch a video. But you can imagine it's the same interpretation as simple linear regression, but you have to add an additional element. Okay, so let's say we're interpreting the crime regression coefficient, and what we would say it is just like before, as crime increases by 1 unit. Okay, the average median home, as you can see, I'm putting the average in front. Doesn't matter where you put the average. The average median home will decrease by 0.21 on average. Sorry, I put it at the end. Doesn't matter. Wow, you have to add this new element while holding room and age variable constant. So in order for you to interpret each regression coefficient, you have to assume that you're holding the other two explanatory variables constant. That's the only add. And since that's not necessarily why, someone can say why, is because everything is moving in these regression coefficients, right? But in order to actually understand that rate of change for one variable, you have to assume that you're only fixed on that one variable while the other variables are not changing. Okay, while the other variables are not changing. And so that's the logic for all three interpretations. As room increases by 1 unit, crime and age are being held constant. As age increases by 1 unit, the other explanatory variable, room and crime, are being held constant. Okay? Again, the notes are already posted so we can continue. So given the multiple regression model, crime, room, and age fit on the Boston housing data set, suppose we have a suburban suburb with a crime rate of 25, average room of 6, and the proportion of owner-occupied homes built prior to 1940 is 35%. What would be the median home value? So before we even make this prediction, what must we do? We need to make sure that 25, 6, and 35 are within the min and max of the data. 25, 6, and 35. 25 is in between 6, is in between 35, is in between. Good to go. So we can now make that prediction. Hopefully y'all laugh when I do things like that. If it's not, it's fine. Y'all don't laugh at class, so whatever. So once we know that's in between the min and max, we can now put that into the equation. It's 17.57. So then how we would interpret this is that when a home has a crime rate of 25, an average of 6 rooms per dwelling, and a proportion of occupied units built prior to 1940 is 35, the average median home value is $17.57 thousands of dollars. Okay, that's it. Key element, average. Okay, it's an average. All right, shall we proceed? Yes, we shall. All right, so we have a model that's trying to predict the median value of owner-occupied homes, MED-V, based on crime, room, age. This is done by using a method called multiple linear regression. Okay, the omnibus test is a way to check, okay, if the whole model is useful. Okay, it's like asking, does these factors, crime, room, and age, together help predict the median value all at once? We just see if all of them work at once. So we've done this before, okay, but we'll keep on going. Based on the summary of our fitted model, can we state the null and alternative hypothesis for omnibus test? We already wrote this down. Okay, so still, let's write it again. Okay, with the null hypothesis, okay, it's F distribution. And we should have known that again on the quiz from the fact that it says F value. Okay, and I said that on Wednesday. The null hypothesis would be that all the regression coefficients are equal to 0. The alternative would be at least one of the explanatory variables has a linear relationship with the response. Saying the null hypothesis in words, all of the explanatory variables do not have a linear relationship. I need to see that word linear relationship with the response variable. Okay, and then this is it with context, and this is it with the same with context. We provided the test statistic, provided the p-value. Based on the p-value, we're going to decide to reject the null hypothesis, indicating that at least one of the explanatory variables has a linear relationship with the response. Okay, or in this example, context, which is needed, at least crime age, or room has a linear relationship with median home value. All right. So with that being said, now let's say we want to, test the non-alternative hypothesis for one of the regression coefficients once we already rejected the null hypothesis for the omnibus test. We can then do that. Similar to simple linear regression, the null hypothesis would be that beta 1 is equal to 0 versus beta 2 is not equal to 0. If it wasn't crime, you would take beta, if it was age, for example, I think age is the second variable that we specified up here, our room, we would say that beta 2 is equal to 0, which tells me beta 2 is equal to 0 if it didn't say crime, but it said room, okay? But since it said crime, we'll say that beta 1 is equal to 0 versus beta 1 not equal to 0. This distribution, as I said, t value, that's going to be the t distribution that we use. And this is the non-alternative hypotheses using words, okay? Crime does not have a linear relationship with median home value. And then alternative is that crime does have a linear relationship with median home value. And it doesn't matter the order, okay? It doesn't matter the order. All right, so here's the test statistic. Here's the p-value, okay? We're going to decide to reject that null hypothesis, okay? We can also create a 95% confidence interval. You use the critical value of 1.96. It's the same equation as before. Okay, we have negative 0.27 all the way to negative 0.144. You notice that 0 is not within the bounds, which agrees with our hypothesis, our decision regarding our null hypothesis, right? Because we're testing if it's plausible to be 0. 0 is not plausible since the interval, since this test statistic is really large, the p-value is extremely small. It makes sense that in terms of our actual range of plausible values, 0 is not within its bounds. Okay. All right. So in terms of model metrics, okay, we have the standard deviation of residuals, okay, SE, which is 6.094, and this tells us how. There's a lot of ways of saying this, okay. It tells us how far each point deviates from the regression equation, not the regression line, on average. Measures the amount of unexplained variability. Okay, remember the line is supposed to be the prediction, all right, to explain the variability, whereas the point is just the data. So what's left unexplained is going to be the distance from the point and that line. If you ever go on to take 324 or other stat classes, you get to see that and measure this, see this equation, which is quite nifty. Again, it's important because it measures how well the model performs or will perform, and you can use this metric to measure across multiple models. And ideally, as we mentioned in class, the smaller the better. Smaller the better. Okay, maybe you're not that excited, but I am. All right, so finally, the adjusted R squared. So when it comes to multiple linear regression, we have to understand that there are times when you can just add explanatory variables to a model and the R squared is going to superficially increase. Okay, it's either going to stay the same or superficially increase just because of randomness. Okay, if I use study hours to predict your GPA and I randomly use your hair length, right, that could potentially by chance increase the R squared, okay, meaning that a higher proportion of variability is explained by the model. But using hair length does not predict your GPA, because I'll be short. Have I used that joke already? Because I'll be short. So ideally, we should penalize the R squared for us using explanatory variables that don't necessarily increase the R squared. Again, is there an equation? Yes. Are we going to see it? No. So here, I'm going to articulate that we use the adjusted R squared for multiple linear regression to counter adding additional explanatory variables that don't necessarily add or explain more variability in the model. So it's just a way for us to counter adding erroneous, or just for lack of better terms, nonsensical explanatory variables to a model just to increase the R squared. Okay, so it's a way for us to penalize the R squared for adding variables that don't make sense to the model that don't necessarily add substantial amount of variability being explained. Okay, so that is that. Okay, it has the same interpretation. It has the same interpretation. So it measures the proportion of variability in response that explained by the explanatory variables. Okay, that's it in words. Okay. All right, and so the adjusted R squared accounts for multiple explanatory variables within the regression equation, whereas the R squared does not. Another model metric, which we already mentioned already, would there be any issues of multicollinearity or explanatory variables being seen in this situation? And the idea is no, because remember the VIF measures multicollinearity, and all these values are in between 1 and 4, and where the lowest is 1, that is possible, and the highest is infinity, and we say anything in between 1 and 4 is fine. Okay, so there would not be an issue. Would there be an issue? So there's no. Sorry about that. This should be a no, because it doesn't exceed 4. What's the difference between multiple linear regression and simple linear regression? Multiple linear regression has multiple explanatory variables, whereas simple linear regression only has 1. That is it for today. Thank you. Oh, well, it for this video. I have another one to make. It's just a review of this material some more in a different context, and that is about it. Thank you for watching.